We've completed our study of parametric equations and calculus in parametric equations. We now turn our attention to a different kind of coordinate system called the polar coordinate system. When we're dealing with polar coordinate systems, these are better for things describing the motion of objects that are rotating about some fixed point. So this could be like the planets or a comet moving around another body in space under the influence of a gravitational field. It could also be some particle acting under an electromagnetic field, or even electrons moving about the nucleus of an atom. So when we talk about these things, we're typically talking about circular, elliptical, or hyperbolic paths. So when we're talking about those, or it could even be parabolic, those are, of course, conic sections. So the culmination of studying polar coordinate systems is going to be to take the conic sections and study them in this new coordinate system. The first thing we want to do, though, of course, is compare the polar coordinate system to the rectangular or Cartesian coordinate system. The rectangular coordinate system was named for René Descartes, which is why it's called the Cartesian coordinate system. And it's based on rectangles. In other words, you have the x-axis and the y-axis, and they're at right angles to each other, and it creates this rectangular grid. And when you're giving the coordinates of a point, you're relating their distance from the x-axis for the x-coordinate and the y-axis for the y-coordinate. So when you give an ordered pair A, comma B, you're getting the distance from each of those axes. Now, when we're giving the coordinates of a point in rectangular system, the first coordinate given always represents the independent variable. So when we write x comma y, x is the independent variable, y is the dependent variable that depends upon the value of x. When we look at the polar coordinate system, we're going to see that the polar coordinate system is actually quite different. In the polar coordinate system, when we give the values of the coordinates, we give them in the reverse order. So we give the dependent variable first and then the independent variable. The polar coordinate system is not based on a rectangular system like the Cartesian system or rectangular coordinate system you see on the right. Instead, the polar coordinate system consists of a series of concentric circles. Concentric means with the same center. So we have basically what looks like a target shape. If you're going to do archery or shooting or something like that, it looks like a target. The origin is called the pole. So the point that corresponds to 0, 0 on a rectangular coordinate system becomes what we call the pole on the polar coordinate system. Unlike the rectangular, which has a line extending from the left to the right as the x-axis, and a line extending from the bottom to the top, which we call the y-axis, the polar coordinate system only has one axis. And it is called the polar axis, and it is not a line. It's in fact a ray. So it has a ball at one end, starting here at the pole, and extending to the right along what would be the positive x-axis if we superimposed one on top of the other. We still label the quadrants in the same way. So if we superimpose an x and y axis on top of the polar coordinate system, we can still call these quadrant 1, 2, 3, and 4. But again, we're calling the origin now the pole, and we're calling the positive x-axis the polar axis. Let's go ahead and talk about some of this terminology. When we talk about the terminology, we need to define what we mean by all of these different things. So let me share my screen with you so you can read it more carefully. Share screen and done. Okay, so now when we're looking at this, we want to define the polar axis, which again is a ray corresponding with the non-negative x-axis, starting at the origin or the pole and moving off to the right. We call the point end of it the pole, which corresponds to the origin. And this is a fixed point in space around which, if we're describing something moving along a conic section path, the focus of one of those points would be at the pole. And so the pole becomes sort of a fixed point around which objects could be moving under the influence of some electromagnetic field or gravitational field or something like that. Now we want to define what we mean by the coordinates when we're in the polar coordinate system. So what we want to define now are the radial and angular coordinates. So the polar coordinates are not given in the typical order. We don't give the independent and the dependent, we do the other. So the first variable that's given in the coordinates is r, which is called the radial coordinate. This is actually the dependent variable. And it represents how far that point is from the pole as if it were on the radius of a circle. So if we look back up here on our system that we have right here, if I were to draw a point, say right here, then this distance right here from the pole to there would be r. So again, it's the distance, straight line distance from the pole to the point. All right. Now we measure this as if it were the radius of some circle. And in fact, this is on the 1, 2, 3, 4, 5th concentric circle. So r is equal to 5, as if it were a radius. And in fact, that's more or less what it means. Now let's define the angular coordinate. The second variable that's given is actually the independent variable. So it's backwards to what we do in rectangular coordinates. The second variable given is theta. So the value of r depends on the value of theta, not the other way around. Theta is called the angular coordinate, and it is measured from the polar axis moving counterclockwise to the radial arm that extends from the pole to the point. So this would be that angle. So let's go back up above and let's see how that would measure out. So you go in a counterclockwise direction from the polar axis, which is here to the right, up to the radial line from the pole to the point, and that measures theta. Now, of course, we could go clockwise. If we go clockwise, it does what you expect. It would be a negative angle. So moving in the positive direction is moving counterclockwise. Now we can see here in this graph the relationship between the points on a rectangular coordinate system and the point in the polar coordinate system. So in the rectangular coordinate system, point P corresponds to the coordinates x, comma, y. However, point P can also be given in the polar coordinate system, which would also represent, and again, we do this in the order r, comma, theta. So we have P of r theta. So that's the value of the point in the polar system. So we have this relationship that we have going on here. Now, this, of course, forms a right triangle. You know this is going to be a right angle right there because this dashed line that's labeled y is parallel to the y-axis, so it is perpendicular to the x-axis. And this gives us some relationships that we can see from this triangle between x, y, r, and theta. Let's go ahead and write down what some of these relationships are. We're going to use right triangle trigonometry. We're going to say that the sine of theta is equal to y over r. And we can say that the cosine of theta is equal to x over r. Right? Again, the adjacent side divided by the hypotenuse. They've labeled it up top, but of course you can label it down here as well if that makes you happier. And then we have tangent of theta, which is going to be the y over x value, which relates y and x to theta without relating it through r. But because it's a right triangle, we also can use the Pythagorean theorem, which tells us that x squared plus y squared will give us r squared. So we can see from this relationship that we have some relationships between the points in the rectangular system and the point in the polar system. Now we're going to take each of these values right here, and we're actually going to solve for x and y out of the first two. So if I solve for x and y out of the first two, I get a slightly different relationship. This leads to y equal to r sine of theta. And this one, of course, leads to x equals r cosine of theta. So now I know what the x and y coordinates are in terms of the coordinates in the polar system. And again, tangent of theta is still y over x, and x squared plus y squared still equals r squared, which gives us a way to relate r to x and y without the angle theta. Now we are going to look at this particular version of the graph. This is the one that we saw before, which is basically the polar coordinate system with the x and y axis superimposed on top of it. That's often enough for us to do our graphing. We don't need more, but sometimes we do. And specifically, what we often like to have are the actual angles. So we'll mark off the angles as we move around this thing here, and you'll see that they draw lines like the spokes of a wheel, which represent that radian measure. So this is the angle pi over 12 moving in a counterclockwise direction from the polar axis. This is the pi over 6 line, pi over 4, pi over 3, 5 pi over 12, pi over 2. You'll also see that it has one of these concentric circles colored blue. These are the better kinds of graphs that you'll find. It makes the multiples of 5 in a different color. So the blue one corresponds to the 5th concentric circle out from the center. So for example, if we were looking at this green dot, I would say that it's on the 5th concentric circle at the angle of pi over 6. So I would give 5 for the radius and pi over 6 for my angle measure. And that's what we want to take a look at next. We want to plot these points in polar coordinate systems. Now, this is very different from what we saw in the rectangular coordinate system. In rectangular coordinates, the point is unique. If you go to -3, 5, so left 3, up 5, there's no other name for that point. That point is uniquely -3, 5. Polar coordinates are not unique. There are infinitely many names for the same location on a polar coordinate system. So why would that be the case? Let's look at this one that we named just a minute ago. I said it's on the 5th concentric circle and at the angle pi over 6. So I could write the ordered pair 5, pi over 6 to represent it. Now, what if I were to go backwards instead of going pi over 6? I started the polar axis and I went clockwise, but I rotated all the way around until I reached the same radial line. In other words, I came back around to here, which would be 11 pi over 6 in the negative direction, or -11 pi over 6. Well, that would still put me on top of the green point. So I could also name this one 5 -11 pi divided by 6. In other words, I could go backwards and still stop on the same radial line. And this gives me another name for exactly the same point. Well, could I also, again, go forwards, but go around one full time and then another pi over 6? So that would be 13 pi over 6, 5, 13 pi over 6. And yes, you can. So that's another name of it. Now, how many times can you go forwards and backwards and keep making one full revolution plus pi over 6? Well, infinitely often. So there are infinitely many names for this location in green on the polar graph. So polar coordinates are not unique. In fact, what you're going to find is if r theta is on the graph, then going around some multiple of 2 pi added to that angle theta will still be a good name for that point. And going backwards by a multiple of 2 pi, subtracting 2 pi in from theta, will also put you at the same point, right? Now, we've seen that the angle can be negative. What about having the radius be negative? And what does that even mean? And how can you have a radius of -3? Well, a negative angle means what it does in trigonometry. It means rotate clockwise. A negative radial coordinate, r, means that we instead move out in the opposite quadrant. So 1 and 3 are opposite, and 2 and 4 are opposite, along the 180-degree line. So if we're looking at that, coming up here, the 180-degree line is the one you see highlighted here in brown. So again, if the point were here, making the radius negative would, instead of plotting here, shoot it out along the line into quadrant 3 along the 7 pi over 6 line, which is the 180-degree line attached to pi over 6. And that's what happens with a negative radius. When you have that, that basically means then that negative r theta is the same thing as having positive r and moving that angle around 180 degrees or pi radians, theta plus pi or theta minus pi. And those would also be good names for it. So let's go ahead and practice what this would be. Let's say we did -3 comma pi over 3. Well, according to this formula that you see down here, this has to be the same as 3, and then taking pi over 3 and adding pi to it. So pi over 3 plus pi would be pi over 3 plus 3 pi over 3, which is pi, which would leave you out here at 3 comma 4 pi over 3. So the way to graph it or plot it when you have a negative radius is to change the value of the radial coordinate into a positive and to shift it around in the 180-degree line by adding pi, or you could subtract pi. So another name for this would also be 3 comma pi over 3 minus 3 pi over 3, which would give us 3 comma -2 pi over 3. Now let's see where those 2 points would plot. 4 pi over 3 should be on the third concentric circle along the 4 pi over 3 line. So here's my 4 pi over 3 line. And notice that it does connect. So let me highlight it here. It does connect with the pi over 3 line, all right? So it makes a straight line there. And what did we say? -3 pi over 3 graphs on the third concentric circle, 1, 2, 3, but in the 180-degree opposite direction, which is there at 4 pi over 3. Now, if I went -2 pi over 3, I'd be going backwards, which would put me in exactly the same place. So there are lots of different ways of naming the same point, right? And we've seen 3 of them here, right? One with the negative radial measure, one with a positive moving by pi forward, and one with a negative angle moving pi backwards, right? So looking at this particular value here, if we have a point here and we're graphing the point 4 comma pi over 3, that's what this is right here in this red color. That's the point 4 comma pi over 3. How do we know? It's on the 1, 2, 3, 4th concentric circle. So R is 4. And this is the pi over 3 radial line. Now on this particular graph, the angles aren't marked. So it does help to go ahead and write down what they are so that you can kind of see. The one that's halfway across, of course, is pi over 4. This is pi over 12 and pi over 6 and pi over 4. And I think, if I'm counting right, and then we've got pi over 3. It looks like they may have it, yeah. And then pi over 3, and then a multiple of 5 pi over 12. All right, so when we're looking at this particular one, what are some other names for that point? Well, I could go around one entire circle and then go back to pi over 3, which would give me 7 pi over 3. I could instead go backwards and come around -5 pi over 3, and that would put me here for -5 pi over 3. Or I could graph it with a negative radial point. So I could graph -4 pi over 3. Now, 4 pi over 3 is down here in quadrant 2 along this blue dashed line. And so -4 would shoot it out 180 degrees in the opposite direction along the pi/3 radial line at the fourth concentric circle. So there are lots of different names that we could use for this. I could also use -4, -2 pi/3, and that would plot the same point. Again, we would be coming around -2 pi/3, which would put us here in quadrant 3 along the fourth concentric circle, but it's -4, so we shoot out 180 degrees opposite and plot it on the fourth concentric circle along the 180-degree line in quadrant 1. All right, now let's go ahead and do some examples. We've already done this one several times. This is the one that we started with. This is on the fifth concentric circle. So this is 5 pi/6. And it would be the same thing if I went all the way around and then stopped again at a multiple of pi/6. So this is 5, 13 pi/6. Or I could make this 5 go backwards, which is clockwise, which would make it 11 pi/6. Or I could make it a negative radius, and that's going to put it on the 180-degree line, which is going to be down here at 7 pi/6. So I could graph -5, 7 pi/6. Or I could graph -5, comma, and then what would that be? -5 pi/6. So again, -5 pi/6, -3 to here, and then 2 more puts us out here. And then the negative radius shoots us out 180 degrees opposite, and we end up over here. Okay, let's take a look at the next example, which is number 2. This time I've not plotted the point for you. Instead, I have just given you the coordinates 6, pi/6. So go ahead and plot the point and come up with multiple ways of representing it. Pause the video, do the work, then turn the video back on, and we'll compare our answers. So again, that 180-degree line goes through pi/6 and 7 pi/6. So if the radial measure is negative, it's going to shoot out in the opposite direction from quadrant 1 to quadrant 3 or quadrant 3 to quadrant 1. So -7 or -6, 7 pi/6. 7 pi/6 is here in quadrant 3, but the -6 will shoot me out on the opposite side on the 6th concentric circle, which of course would be right here. All right. And so I've got all of these different names which correspond to that particular point. Let's take a look at the next example. Go ahead and pause the video, work out the different names for the point and plot the point, then turn the video back on. So this particular one has a negative radial measure from the beginning. It's along the -pi/4 radial line. So we find -pi/4 by moving clockwise pi/4. And because the radius is negative, we draw the 180-degree line. It's going to shoot out into quadrant 2 along the 8th concentric circle, which I don't have 8, I only had 7, but it would be the next one out, so it would be there. And these all give different names for the same point. All right, let's take a look at one more example. This is the point 0, -pi. Pause the video, do the work, turn it back on, and let's compare. This one is kind of an interesting point. By having the radial measure be 0, it means we never move away from the pole. So it really doesn't matter what the angle is, we're not moving off the pole. So bizarrely, you can give any angle measure with a radius coordinate of 0, and it's still going to plot the pole. In other words, this is also 0, 0, which we see right here as one of the choices. But again, you can completely change the angle. It doesn't matter. The radial coordinate is 0. It is the pole. So unlike in rectangular coordinates, where 0, 0 is the unique name of the origin, there are infinitely many names of the pole. And what we're going to see is that it may actually have a curve that traces itself more than once. And the different angle measures tell you when it reaches the pole on that particular time it crosses through the origin. So in a sense, it's like the parametric. It's telling you when, or rather at what angle, it reached that coordinate again. Okay, let's now look at the relationship between rectangular coordinates and polar coordinates. When we did this earlier, remember that we had the relationships up here. So let me see if I can find those again. They were right here. So we did the relationships between x, y, r, and theta by using this right triangle and representing the point x, y in polar coordinates as r theta. R being dependent, theta being independent. So R depends on theta, backwards from what we do in the rectangular coordinate system. And this gave us the relationship that y equals r sine theta from the basic definition of sine, x equals r cosine of theta from the basic definition of cosine, the definition of tangent, which relates y over x to theta, and the Pythagorean theorem, which tells us that x squared plus y squared equals r squared. So we have these relationships then between the different points on the graph. And this gives us these equations that you see down here at the bottom. Now, these are the ones that we're going to use to convert from one system to the other and back. So we're going to use these 4 equations that you see at the bottom whenever we need to convert from one system to the other. And there are some reasons to do the conversion. For one thing, it helps to go back into rectangular so you can recognize what kind of graph you have, but it may be easier to graph in the polar system, maybe a simpler equation in the polar system. And we're going to see that when we look at a circle. The equation for a circle in the polar system is super simple. It's just r equal a constant, and that gives us a circle. And you know that in the rectangular coordinate system, you have to have x squared plus y squared equals the radius squared, which isn't nearly as simple as r equals 4. All right, so let's say that we're given a point P in the Cartesian system, the rectangular, with coordinates x comma y and polar coordinates r theta. How do we convert from one to the other? We use one of those 4 equations to convert. Now, when we're doing this, sometimes it's helpful to have the rectangular axis superimposed on top of the polar axis so that you can see the relationship between the two. You may or may not include the labels on the angles. If you don't, you'll have to count the radial lines to be sure you know which one is which. The one in the middle is always the multiple of pi over 4. And usually they're marked off either in pi over 12 or pi over 6 multiples. Then sometimes you'll see that it actually superimposes them. This is one that I did and created for my students. And it has spokes at the major angles, pi over 6, pi over 4, pi over 3, and pi over 2, and all of their multiples as you move around the unit circle. It also gives you the multiples, the concentric circles up to the 10th concentric circle, and it superimposes it on a rectangular coordinate system. So note the 3 pi over 2 and pi over 2 line is really the y-axis, and the pi 0 line is really the x-axis. The polar axis is from the pole, the origin, off to the right, and it's marked there in red. So let's go ahead and find the rectangular coordinates of this point, which is given in polar coordinates. So we have the polar coordinates here, which are 7, 2 pi over 3. So where would that be? Well, again, this represents r, and this represents theta. So we're on the 7th concentric circle. So you can count out 1, 2, 3, 4, 5, 6, 7. And we're along the 2 pi over 3 line. R is positive, so we stay in that quadrant. We don't shoot out in the 180-degree line. So this is our point right here. I can tell just by looking at the rectangular that it must have a negative x coordinate and a positive y coordinate. I can't even estimate that it's somewhere between -3 and -4 and very close to 6 for the y value. But I want an exact value for it. So how am I going to get the exact value? I'm going to use this equation right here and this equation right here to get the exact values of x and y. So x is equal to 7 times the cosine of 2 pi over 3. Now remember, the 2 pi over 3 is the tall, skinny triangle. So this side has to be square root of 3 over 2, and this side is negative 1/2, right? If we're looking at the Pythagorean theorem based on the unit circle. So the cosine of 2 pi over 3 is going to be a negative 1/2. Cosine gives you the x value. So you have 7 times negative 1/2, which is a negative 7/2, which makes sense. I said it was between -3 and 4. It's exactly in between. It's negative 3.5. And then I find the y coordinate using the other equation. So I have 7 times the sine of 2 pi over 3, which turns out to be 7 times the square root of 3 over 2. And that becomes my y coordinate. So I have negative 7/2 or negative 3.5 and 7/2 the square root of 3. And those are the coordinates in the rectangular coordinate system. Let's take a look now at the next one. This is, we want to again find the rectangular coordinates for a point in polar coordinates. This time our point is -7, -17 pi over 6. Now, you're going to have to do a little work on -17 pi over 6 in order to know where it is. Remember that 12 pi over 6 is 1 full revolution, and negative means we go backwards. So 1 full revolution takes me 12 pi over 6, and then I'm coming out another 5 pi over 6 in the negative direction, which would put me over here on the 7 pi over 6 line in quadrant 3. But the radius is -7, so that's going to shoot me out on the 180-degree line into quadrant 1 along the pi over 6 radial line on the 7th concentric circle, which is here in the red dot. Now the 180-degree line is highlighted here, dashed in brown. So again, we want to convert the coordinates. So when we're looking at this, we're going to write x is equal to -7, the cosine of -17 pi over 6, and y is going to be -7, the sine of -17 pi over 6. Now remember that if angles are coterminal, we can use the smaller angle to find the trig values for it. And in fact, this one over here is coterminal, of course, with pi over 6. So if we're looking at these and we want to evaluate what they are, this basically, if I evaluate this, if I go around, this was coterminal with -5 pi over 6. So this becomes -7 cosine of -5 pi over 6. Now that's not in quadrant 1, that's over here in quadrant 3. So there's my 12, and then 5 more puts me out here, right? So I have that triangle right there. Now pi over 6 is the long short triangle, which means that this side right here has to be negative the square root of 3 over 2, and this side is a -1/2. It's in quadrant 3, so they're both negative. Now, when I evaluate the cosine of that angle, I'm getting the cosine of -5 pi over 6 and the sine of -5 pi over 6. So this is going to give me a -7 times a negative square root of 3 over 2, which is going to give me a positive value, which is what I was expecting because my point ended up here. So my point becomes 7 square root of 3 over 2 for the x coordinate. And the y coordinate, again, the sine of -17 pi over 6 is the same as the sine of -5 pi over 6, which puts it in quadrant 3. It's a -1/2. So I get -7 times -1/2, which is a positive 7/2 or 3.5. And then if I were to do the decimal approximations, I would find out exactly what these values are, and I could see that they are exactly there on the grid where I thought they would be. All right, so it's definitely up here at 3.5, and it looks like 7 squared root of 3/2 is just past 6 on the rectangular coordinate system. Okay. This time, we want to find the polar coordinates for a point given in rectangular coordinates. So that's no longer our theta. This is now x, y. So in order to find that one, what we need to do is we need to find something to do with r and something to do with theta. Well, at the beginning, all I have is x and y. I don't have a theta. So to look at this, what I'm going to do next is I'm going to take the only equation that doesn't have theta in it, and I'm going to say that x squared plus y squared has to give me r squared. And in that sense, I'll be able to come up with an r. So let's take a look at this one. So I have x squared plus y squared equal to r squared. Now, when I'm looking at this particular value right here, I can get 2 square roots of 3 quantity squared plus -2 quantity squared. And that doesn't give me r, but it does give me r squared. So 2 squared is 4, square root of 3 squared is 3, -2 squared is 4, and this is going to be r squared, so I'm getting 16. Which tells me that r could either be 4 or -4. And again, we can always measure in an opposite quadrant, shooting out the 180-degree line by making the r value be negative. To make it simpler, I'm just going to assume that r is 4, but again, I could do it for -4 as well. Now I need theta. Well, then I need something that relates x and y to theta only, which would be the tangent right here. So if I'm looking at this, and again, I could use one of these two equations because I now have a value for r, so I could use one of these as well. But tangent of theta is probably one of the easier ones to use. So if I'm looking for theta, theta is going to be the arctangent of y divided by x. So theta must be the arctangent of -2 divided by 2 square roots of 3. And that's going to give me the angle whose tangent comes out to be -1 over the square root of 3. Now I'm going to have to use my knowledge of where I am in the rectangular system to figure out whether I need to use values in quadrant 2 or values in quadrant 4. Clearly I'm in quadrant 4. So I want to look at the angle in quadrant 4. All right, if I were in quadrant 2, where tangent's also negative, I'd be looking out there. Now, what angle gives me a tangent of 1 over the square root of 3? Well, it's got to be a pi over 6, pi over 3 thing, because I've got a 1/2 over root 3 over 2, and this is sine over cosine. So it's got to be a short y angle and a long x side. So again, the triangle that you're looking at is this one right here, where this is a short y side, -1/2, and a positive x side, the square root of 3 over 2. And we know that because that one is the long short triangle, that it's a multiple of pi over 6. We're moving backwards into quadrant 4. So I could either call this -pi over 6, or I could go all the way around in the positive direction and call it 11 pi over 6. Either one of those would work. So in polar coordinates, I could call it, oops, I forgot to put the 4 -pi over 6, or I could call it 11 pi over 6, or again, I could shoot it out into quadrant 2 with a negative radius, and that would push it back into quadrant 4. So you can call it lots of different things. Let's take a look at one more example. This is example number 8. Again, these are rectangular coordinates. So this is x comma y. So go ahead and pause the video, work out this example, then turn the video back on and we'll compare our work. So again, we apply the equation x squared plus y squared equal r squared to get values for r. R turns out to be either 6 or -6. First, I'm going to look at r equals 6. I find the angle whose tangent is y over x, which when I reduce gives the arctangent of the square root of 3, and it's negative. Now, arctangent is only going to give me a value between -pi/2 and pi/2, so it spits back the value -pi/3. But I know from looking at the point in rectangular coordinates that it's not in quadrant 4, which is where -pi/3 is. So get it into quadrant 2, I add pi to it by adding 3pi/3, which gives me 2pi/3. So I can use the positive radius value, 6, with the angle 2pi/3, or I could use the negative radius value, -6, with the angle -pi/3 in quadrant 4. And then because the radius is negative, it's going to shoot it out on the 180-degree line. Now we want to move on to something slightly different. This is what I call more of a play section, where we're going to identify the polar curve and identify some symmetry by looking at the curve. Now, you can do these without symmetry, but it definitely does help if you understand the symmetry of some of the polar graphs. So, for example, in example 9, it says identify the polar curve by transforming from a polar equation to a rectangular equation, and all we're given is r equal 2. Now, if you remember what I said earlier in this video, you already know that this must be a circle of radius 2. But how would you get that if you didn't know that? Well, we need something that relates r to x and y. We're trying to get back to a rectangular equation in terms of x and y. I don't have r squared, but I have r. I can get r squared by simply taking this and squaring both sides, and that gives me 4. Then I can replace the r squared with x squared plus y squared, and I get x squared plus y squared equals 4, which is a circle with the center at the origin, radius of 2. All right? And so we see that we can convert what was actually a simpler equation in polar coordinates into its rectangular version, and this turns out to be more complicated. And you can see now why you might prefer instead to use this simpler polar equation, particularly if you're going to do calculus on it. The calculus would be simpler on an equation like this than it would be on an equation like that. Let's take a look now at the next example, which is the polar curve r equal 3 cosine of theta. Now, when we're looking at this one, this is not like the last one. I've got both theta and r. So I don't want to use one that doesn't have both theta and r. So I don't want to use this one on the far right, and I don't want to use the tangent one. It doesn't have r, and x squared plus y squared equals r squared doesn't have theta. That gives me one of these two up here. Well, only one of these has cosine in it. So what I'm going to do is I'm going to solve this equation for cosine and solve this equation for cosine and set the two cosines equal. So from r equals 3 cosine of theta, I can solve for cosine of theta, and I get r divided by 3. And from x equal r cosine theta, I'm going to again solve for cosine of theta because I'm going to substitute and set each of those equal to each other. I get x over r. By substitution then, r over 3 is equal to x divided by r. Now I can multiply both sides by the lowest common denominator, which is 3r, or if you want to think of it like a proportion, you can cross multiply. Whichever way that you want to think about doing this, whether you multiply by the LCD on both sides or you cross multiply, you should end up with something that looks like r squared equal to 3x, right? So now I have something that relates r and x, but I need to get out of R and get only into X and Y. But I know what R squared is. R squared is X squared plus Y squared. So I can replace this with X squared plus Y squared equals 3X. Now, you may not recognize this, but if you've done polar coordinates in the rectangular system, this is the graph of an ellipse, I believe, or a circle that's been shifted. A circle that's been shifted, I believe. All right, so when we're looking at this, this is the circle that's been shifted. What you would have to do to find out where it was shifted is you would have to complete the square on the X part, and then it would equal to 0. So when you complete the square on the X part, you're taking half of the 3, which is -3/2. You're squaring it, which is 9/4. So you add 9/4 to both sides of the equation, and then you complete the square. So this would be X minus 3/2 quantity squared plus Y squared equal to 9/4. So this is a circle with the center at 3/2 0. So it's been shifted to the right. And the radius is 3/2 as well. Right? Let's take a look now at this next example. We want to again convert this one. We have a relationship R equal 4 cosine theta plus 4 sine theta. So we want to do something similar to what we did before. We want to replace cosine theta and sine theta with something from this first equation and this second equation. We're going to hold off on these latter two because they don't involve both R and theta. So when we're looking at this, we're going to replace cosine of theta with X over R. And we're going to replace sine of theta with Y over R. So this then becomes R equals 4 times X divided by R plus 4 times Y divided by R. Now, you've got fractions on the right side. They have the same denominator, which is R. So I can multiply the entire equation by R. That will eliminate the 2 R's on the right, and that will give me R squared on the left. So leading to the next line, I get R squared equals 4X plus 4Y. And R squared can then be replaced with X squared plus Y squared equal 4X plus 4Y. And again, what we see is this is going to be a circle, and it's probably been shifted. So if we were going to want to put it, now this is fine to leave it in rectangular, but if you want to see what the circle equation is, then you write X squared minus 4X plus Y squared minus 4Y equals 0. And then we complete the square by taking half of the -4, which is -2, square it, which gives us 4. So we're going to add 4 here and add 4 here. And then I'm going to do the same here because it turned out to be the same pattern. And so I get 8 on that side. When I factor this left side for the X variable, I get the quantity X minus 2 squared plus the quantity Y minus 2 squared equal to 8. So this is a circle which has a center at 2, 2, and a radius of 2 square roots of 2, or the square root of 8. Let's take a look now at the last little bit we want to talk about, which is graphing polar curves by hand. Now, I tend not to ask my students to do this on any kind of test or quiz or anything. It's good practice for starting to get a good feel for them, but it's super long and very tedious. Now, you can do it by making either a theta R or R theta table. I recommend that you write it in the order R theta, even though the theta values are chosen first. That's because theta is the independent variable. And the reason is because the ordered pair is given in the order dependent variable, independent variable, R comma theta. So you would basically go through, you would plug in theta equals 0, figure out what R is, plug in theta equal pi over 6, figure out what R is, so on. Connect the points smoothly. So once you've got them plotted on the polar graph, connect them smoothly. be aware that the curve could retrace itself. It could come around multiple times. It could hit the same point over and over again like this, where it's coming back here to the center several times. That's a very poorly drawn rose, all right? And we'll see these coming up in our next video. We can use symmetry to help us sometimes. So let's take a look at what symmetry for a polar equation looks like. Now, we've got basically 3 different types of symmetry. So the first type of symmetry have is basically x-axis symmetry. So the graph, in fact, folds on top of itself like this. Now, that's great if we're in the XY system, but we're not. We're in polar coordinates. So how do we interpret folds on the x-axis in terms of polar coordinates? Well, it turns out that this is the same thing as replacing theta by negative theta. And if that doesn't change the equation, then you know that it has symmetry across the x-axis. So if r theta is on the graph, then r negative theta is also on the graph. So you can see here, you've got the same radius on both of these. And this is the positive angle, and this is the negative angle. So this is r theta, and this is r negative theta. And they're both on the graph. An example of this is something called a limacon, which is basically what this is here. It comes around in a sort of heart shape, and depending on the value of the limacon, it can make an inner loop. It either makes sort of a dimple, or it makes an inner loop here and then continues on around. So it's sort of a heart shape called a limacon. It's a little more rounded on the bottom than a normal heart, but that's what it looks like. This is the limacon 3 plus 4 cosine of theta. That's one kind of symmetry. The next kind of symmetry that we can have would be folding on the y-axis. And this one is if we replace theta with the supplementary angle pi minus theta. So if theta is, say, 60 degrees, then we replace it with 120 degrees, which would be 180 minus 60. So in other words, if this is pi over 3, we replace it with 2 pi over 3, because those angles are symmetric across the y-axis. So we're basically looking at the supplementary angle and the angle. In this one, if r theta is on the graph, then r pi minus theta is also on the graph. So in other words, the reference angle for both of these is theta, right? So the reference angle here is pi over 3, and the reference angle here is pi over 3. Again, these work when you fold on the y-axis and it lays on top of itself. This is still a limacon. You can see you've got the inner loop here, but this one is oriented vertically, and notice that this changed to sine. Sine controls y, and notice that it produced a vertical limacon, whereas this one with cosine produced a horizontal limacon. No, that's not accidental. That's a pattern that you see developing there. And then we have one more type of symmetry, which is symmetry about the pole, or in other words, symmetry about the origin. So we have the same 3 types of symmetry that we have in the rectangular coordinate system. X-axis symmetry, replace theta with negative theta. Y-axis symmetry, replace theta with the supplementary angle, pi minus theta, doesn't change the equation. And then we have origin symmetry. For origin symmetry, it actually is somewhat easier here. We replace r with negative r. In other words, you're shooting out on that 180-degree line, and it will produce an equivalent equation. So if r theta is on the graph, then negative r theta is also on the graph. So you can see this point right here. This looks like it must be 1, 2, 3, 4, 5, 8. That's weird. Okay, 8. Oh, no, that's on the 4th concentric circle. They're labeled. Okay, 4th concentric circle, and it's at pi over 4. Right? And then looking at this one over here, negative 4 pi over 4 is another name for this point right here. Remember, pi over 4 would send it in quadrant 1, but then because r is negative, we go out on a 180-degree line, which actually plots it down here in quadrant 3. This is what's called a Limnus Gate, which has a figure 8 shape, and it's Pretty obvious when you have r squared equal to something with a trig function. 16 sine of 2 theta gives us a Limnus gate. So this is basically what we wanted to cover in this video. We're just covering the introduction to polar graphs. We are not really going into any depth into polar graphs. We'll go into depth into different types of polar graphs in the next video, but that's mostly just for play, just because they're beautiful and you should see some different types. So we're going to do another video on types of polar graphs. And then, of course, we're going to do calculus with polar coordinate systems. I hope you'll join me for the next video.